Today I've got two exciting updates for you from the last time. First, I bought a fancy new light, so you can see my face in glorious HD. And second,
a shiny new microphone, so you can hear every awkward pulse in crystal clear detail.
You are welcome. Magnetic fields. What could they possibly have to do with electricity? When someone says magnet, most people picture a fridge magnet or maybe a toy. But connected to electric current? Very much so. At the start of the 19th century, electricity and magnetism were seen as two completely separate phenomena. Scientists studied them independently, until Danish physicist Hans Christian Ørsted stepped in. Sorry, Danish. During a lecture, he noticed something strange. When he turned on the current in a nearby wire, the needle of the compass has moved. It wasn't a mistake. It was a solid proof that a current affects magnetic fields. And with that observation, a new era began. Electricity and magnetism were no longer treated as separate things. Ørsted has shown that electric current in a wire creates a magnetic field around it. The discovery eventually led to the development of electric motors, transformers, and the entire world of electrical engineering as we know it today. Magnetic fields can arise in three different ways. First, from the movement of charged particles outside solid materials. For example, a free moving electron. Second, from a current flowing through a conductor or semiconductor. We are classing electric current in a copper wire. And third, from the motion of electrons within atoms, which is what gives rise to permanent magnets. Even though these are quantum effects, the core idea is still the same. Moving electric charge creates a magnetic field, even of the microscopic scale. To get our bearings in the magnetic world, we need to clarify a few terms. Don't worry, it won't hurt, I promise. Once you get the hang of this, everything will start to make sense. Let's start by looking at the key quantities and what they actually mean. First up, magnetic flux density, denoted by the letter B. Think of it as a measure of how strong the magnetic field is in a given spot. The higher the B, the stronger the magnetic force. Basically, how much magnetism is happening there. It's measured in Teslas, named after, you guessed it, Nikola Tesla. And how do you calculate B? Here, mu is the permeability of the material. It tells us how easily the magnetic field can pass through it. It's measured in henries per meter. And H is the magnetic field strength. It describes as how much effort the current is making to create the magnetic field. Measured in amperes per meter, it's calculated like this. Here, N is the number of coil turns. E is a current. And L is the length of the coil. The more turns and the more current, the stronger the magnetic push. Next up, magnetic flux, denoted phi. This tells us how many magnetic field lines pass through a given area. Like how much of the field flows through a wire loop or a piece of iron. It's measured in Webers. named after Wilhelm Weber. The formula is here. S is the area and theta is the angle between the field and the surface. When the field lines hit the surface head-on, the flux is maximal, and when they hit at the angle, it's less. If they are parallel, no flux passes through. 0. Back to permeability. This one's interesting. In a vacuum, permeability is slow. The field passes through easily, but without much amplification. Its value is 4 times pi times 10 to the minus 7th henries per meter. And that's our baseline. In iron has a high permeability, so magnetic fields feel right at home there. Total permeability equals permeability of vacuum permittivity, and it's different for every material. So why are we even talking about this? Because with just a few quantities, B, H, phi, and mu, we can visualize, measure, and calculate what's going on in any magnetic setup. And that's not just handy, it's cool. It helps when you want to understand why your electro engine's buzzing. When a charged particle moves through a magnetic field, it experiences a force. That's the Lorentz force. It's defined as the vector cross product of the particle's velocity and the magnetic field. The result is a force that's perpendicular to both. So while the particle's speed stays the same, its direction changes. It starts to move in a spiral or a circle. The formula is here, where Q is a charge, V is a velocity, and B is a magnetic field. For positive charges, the force points in the direction of velocity times magnetic field. For negative charges, it's the opposite. You might also see this version. This one includes an electric field. It's a more general form, since in real life, both electric and magnetic fields often act together. But for now, we'll focus on a magnetic part. Just like electric fields have field lines, magnetic fields are visualized using magnetic field lines. These show direction and intensity. They always run from the north to the south pole and never end. They form closed loops. At the south pole, they enter. At the north pole, they exit. The denser the lines, the stronger the field. You can see them beautifully with iron fillings around a bar magnet. They align along those invisible field lines. You've probably seen that demo before. But magnetic fields can do even more. For example, if you place a current-carrying wire inside one, the field exerts a real physical force on it. It's called the Ampere's force, named after Henry Marie Ampere, another hero of physics. This force acts perpendicular to both the direction of current and the magnetic field. And if you have two parallel wires carrying current, they interact too. If the current flows in the same direction in both, they attract. If the currents are opposite, they repel. Just like people, them closer, working against each other pushes them apart. And that's it for today. It was a lot, sure. But next time you wonder how your motor spins, how a tram works, or why your fridge magnet sticks. Remember, behind it all is an unexpected romance between electricity and magnetism. From Ørsted's lucky discovery, we've arrived at electric motors, sensors, and even electron spirals in space. Whether it's the Lorentz force or Ampere's magic, it all comes down to moving charge and invisible forces dancing in the air.